Welcome to Algebra 2. Today we have Chapter 10, Day 9, which is going over just some simple probability as well as some geometric probability. To get started, let's go over a couple problems for review. When tossing a coin, what is the probability of getting tails? We've got two outcomes when tossing a coin. We have heads and we have tails. Okay, so out of a total of two outcomes, there's only one outcome in which we can get tails. So that would be 1/2, 0.5, or 50%. When tossing two fair coins simultaneously, what is the probability of getting only one head? All right, we have a couple different outcomes here. If we toss two coins, they could both be heads. They could both be tails. The first coin could be tails, the second heads. The first coin could be heads, the second tails. So in terms of this scenario, we have two outcomes in which we would only get one head out of a total of four. That would be 1/2, 0.5, or 50%. All right, let's get into it. Like I said, we're going to go over probabilities of simple events as well as geometric probability. And our homework tonight is going to be the Chapter 10, Day 9 worksheet. All right, so in example 1, we have an equally likely chance of choosing any integer from 1 through 60. We want to find the probability, in case 1, of a number less than 25 being chosen. All right, so we have to figure out how many numbers are there that are less than 25. That'd be 24, 1 through 24. And then out of the total amount of possible outcomes, which would be 60 different numbers, 1 through 60. All right, so we would simplify that. We get 2/5, which would be 0.4, or 40%. The probability that an even number is chosen would be the amount of even numbers, which would be 30, half are even, half are odd, out of a total of 60 outcomes. So that'd be 1/2, 0.5, or 50%. All right, in example 3, or part 3 here, the probability that we have a factor of 10 being chosen. All right, that would be all the factors of 10 that we have out of the total amount of outcomes. Factors of 10 would be 10, 20, 30, 40, 50, and 60. So that's 6 outcomes out of a total of 60. So that'd be 1/10, 0.1, or 10%. In example 2, we have a spinner. So we want to figure out the probability of the spinner landing on the blue shaded region. This is assuming we have an equally likely chance of spinning any value on the spinner. So that would be the number of blue shaded regions, which is 2, out of the total number of regions that we could land on, which is 8. All right, so that would be 1/4, 0.25, or 25%. The probability that we land on a prime number, so we have to go over our prime numbers. 1's not a prime number, but prime numbers would be 2, 3, 5, and 7. So that's 4 possible outcomes out of a total of 8. So that's 1/2, 0.5, or 50%. And then finally, finding the probability that a number less than 5, or we land on a yellow shaded region. We have to figure out how many numbers are less than 5. So in this case, just count them up. We got 1, 2, 3, and 4. So there's 4 out of 8 events, okay, where we could get a number that's less than 5. And then, or a yellow shaded region. We have 1, 2, 3 yellow shaded regions. So we could add those together. But in this event, notice we have 2 outcomes that we've counted twice. So we have to take those into consideration. Since we've counted those twice, we have to subtract the amount of times we've double counted those events. Okay, so that would be 2 out of 8 times in which we've double counted those 2 events. So we get 5/8, which makes sense. Okay, there's 5 different spots that would be less than 5 or in a yellow shaded region. So 5/8 would be 0.625, or 62.5%. All right, so this example is a good example to figure out what happens when some of those events have outcomes that are in common. So for our OR probability problems, they require obtaining a successful outcome for at least one of the given events. All right, so we have this equation. The probability of event A or B occurring is the probability of event A plus the probability of event B minus the probability of event A and B, which is the number of times both of those events could occur at the same time. All right, so that would be the number of outcomes in which both of those things have in common. All right, note that if the events are mutually exclusive, there's nothing to subtract off because the events cannot take place simultaneously. Whereas in the other example, the two events could happen at the same time. For mutually exclusive events, they can't happen at the same time. So an example of that would be tossing a coin. All right, when we're tossing a coin, we're either going to get heads or tails. We can't get heads and tails. All right, even if that thing lands on its side, we would just flip again. Okay, we're either going to get heads or tails. Now we have 3 geometric probability problems. Now for these, it says find the probability that a dart thrown at the given target will hit the shaded region. All right, there's a lot of assumptions taken into consideration. So we're going to assume that the dart is equally likely to hit any point inside the target. So we're saying we're good enough to hit this square, all right, but we want to figure out what is the probability that it lands in the shaded region. All right, so the probability that it's going to be in the shaded region is simply going to be the area of the shaded region divided by the area of the total figure. Okay, and we're going to just rewrite how we think about the area of the shaded region and the area of the total figure. So to find the area of the shaded region, of course, we could just simply find the area of one of those triangles and then multiply it by 4. But another way to think about it would be taking that total figure and then subtracting out that inner square, or what we're going to call the smaller square, the little square. All right, so it's just the area of the big square minus the area of the little square. Just imagine cutting this inner square, cutting that shape out of the overall square, and then we'd be left with that shaded region. So the area of the total figure is just the area of the big square. So now we have to figure out, okay, how do we find the area of the big square? How do we find the area of the little square? The area of the big square is pretty simple. All right, this part's 8, the other part's 8, so that means the side length of that big square is 16. Okay, so area of the square is just side length squared, so that's just 16 squared. Now we've got to figure out what's the area of the little square. Like we said before, the area of a square is just side length squared, so we have to find that side length. Now if we take a look at this triangle, it's a right triangle. All right, so we could just use Pythagorean theorem to figure out the hypotenuse of that triangle, which would be the side length of the little triangle. Or sorry, the side length of the little square. All right, so that means s squared, the hypotenuse squared, equals 1 leg squared plus the other leg squared. 8 squared is 64. So we have 64 plus 64, which is 128. And if we take the square root, we get the square root of 128. Now if we remember back from factor trees, we could simplify the square root of 128 by taking out that biggest perfect square or taking out the lowest primes. For simplicity's sake, I'm going to take out that biggest perfect square. That's a factor of 128. All right, so the square root of 128 is just the square root of 64 times the square root of 2. And we know the square root of 64 is just 8. So that's 8 root 2. All right, so going back up, the area of the little square is just going to be that side length squared, which is 8 root 2 squared. Okay, and then simplifying, 16 squared is 256. Oops. However, 8 root 2 squared, if we wanted to do that, that would actually be pretty simple. Okay, if we square this value, that just gives us s squared, which is 128. Otherwise, another way to do that would be square 8 and square root 2, and we'll still get 128. All right, so we get 256 minus 128, which is just 128, and 128 divided by 256 is 1/2, 0.5, or 50% chance. So the probability that a randomly selected point in this region lies in the shaded region is going to be 50%. All right, in the second case, once again, the probability that a randomly selected point lies in the shaded region is just going to be the area of the shaded region divided by the area of the total figure. So the shaded region is just a circle, so I'm just going to rewrite this using symbols. So that's just saying area of a circle. The area of the total region is just the area of that rectangle. So once again, I'm just going to use symbols. And now we're just going to figure out how do we find the area of a circle, how do we find the area of a rectangle. Area of a circle is pi r squared, and area of a rectangle is length times width. All right? So we already have the radius, so we can plug that in to find the area of the circle, so that's pi times 2 squared. The length is 5 centimeters, and the width is 8 centimeters of the rectangle. So now let's just do some simplification. 2 squared is 4, so that's 4 pi. 5 times 8 is 40. And 4 divided by 40, or 4 over 40, is just 1/10. So we have pi over 10. If we type that into our calculator and round, and I'm rounding to the thousandth here, we have 0.314, or 31.4%. All right, last geometric probability problem. Like before, just using those examples from before, the probability that it lies in the shaded region is going to be the area of the shaded region over the area of the total figure. And just like before, we're going to use symbols. So the area of the shaded region is just the area of that triangle, and the area of the total figure is just the area of that square. So for a triangle, we have 1/2 base times height. And then for our square, that's side length squared. And let's just simplify. Okay, 3 times 2 is 6. 1/2 of that would be 3. 6 squared is 36. Simplify this and we get 1/12. Okay, and then if we type that into our calculator, we get 0.083, or 8.3%. All right, lastly, last one. Okay, we've got our card problems. So this is using a standard 52 card deck. We want to find the probability that when we draw just one card, we get a face card. All right, that would be the amount of face cards that we have in the deck divided by the total number of cards that we can select from, which would be 52. All right, face cards is a jack, queen, and king, and we can have those of any suit: hearts, diamonds, spades, clubs. So that'd be a total of 12 face cards that are in the deck out of the 52 cards. And if we simplify, that's 3/13, 0.231, or 23.1%. All right, and then in the next one, we want to find the probability of drawing the king of diamonds. So we have to figure out how many kings are diamonds. Okay, how many king of diamonds do we have in the deck? All right, there's one king for every suit. So that means there's only one king of diamonds. So that's 1 out of 52, and if we round that to the nearest thousandth, all right, that's 0.019, or 1.9%. All right, and then a black card in case 3. If we want to find the probability of finding a black card, this might be simple for some of you. Some of you know that in a deck of cards, half the deck is black, half the deck is red. All right, so that's 26 out of the 52 cards, which are black, which would be 1/2, 0.5, or 50%. And then finally, find the probability that when we draw a randomly selected card, that it's a 9. That would be how many 9s are in the deck. Well, we've got the 9 of hearts, 9 of clubs, 9 of diamonds, 9 of spades. So that's 4 out of the 52 cards, which when we simplify would be 1/13, or 0.06, or sorry, 0.077 rounded to the nearest thousandth, or 7.7%. All right, folks, if you have any questions, feel free to email me. And also, very soon, we'll be setting up some kind of live discussion page for class. All right, thank you, and have a good day.